right, so we're going to go ahead and go over all of the things for warm-up of Chapter 14. And so we want to talk about the percentage of cars that are certain things. We know that we have 40% of the cars are made in U.S., 30% of the cars are made in Japan, 10% in Germany, and then 20% of the cars are somewhere else. So, our first question says, what's the probability that a car is not made in U.S.? So that's going to be everything else except for that 40% made in the U.S. So that's going to be your 1 minus 40%. That is 60%. Because it is not, you also could do that by saying the 0.3 plus the 0.1 or the 0.20. So you could do that as well. All right, so we have those two different ways that you could come up with that. Now, next one is it made in Japan or Germany? We know that Japan or is addition. So that or is going to add those two parts together for a total of 40%. So next we have two in a row. So two separate events that must happen at the same time. That's and. First one is Japan and the second one is Japan. So that's going to multiply 0.3s together to get 9%, 0.09. Now we have the situation where we have none of the three cars are from Germany. So there are three events, three trials. The first car is not from Germany, and the second car is not from Germany, and the third car is not from Germany. So of course you can see up here that Germany is 10%, which means not from Germany is 90%. That is how we have 0.9 times 0.9 times 0.9, which is your 72.9%. All right. So now we have, what's the probability that at least one of the three cars is made in the U.S.? So we know the probability of at least one is 1 minus the probability that none of the three cars are made in the U.S. So we have to talk about that probability that none of the three cars are made in the U.S. So that piece in itself, that piece right there, all of that, none of the three cars being made in the U.S. is something we need to go over to the side and compute. So we're going to go over and have all three cars not being made in the U.S. Well, we know that from up above, we recall that 40% being made in the U.S. said there 60% were not. That's where that 0.6 comes from. So 0.6 times 0.6 times 0.6. All three of them are 0.6s. So I do 1 minus 0.6 to the third, and that's how you get your 78.4%. All right. Now, question F is talking about 5 cars. Out of the 5 cars that you picked, what's the probability that the first Japanese car is the fourth one you choose? So what happens is we are defining which vehicle is in the fourth spot. So the first one is not Japanese, and the second one is not Japanese, and the third one is not Japanese, and the fourth one is the Japanese one. Now, even though we are talking 5 cars, we are not told what the 5th car is. It does not matter. It is not told to us. So therefore, we do not have to mess with that 5th car at all. So we multiply all of those numbers together, and that's how we get our 10.29%. Of course, we could see that Japanese was 0.3. That is then why the not Japanese was the 0.7, and then that Japanese one was the 0.3. All right. So now, the second one is asking about disjoint events being independent. So I have previously made an entire video going over and explaining about why disjoint events are never independent. Never are disjoint events independent. So I went into detail on that on a previous video, but I'm going to give you a shortcut of that idea right now. Remember that disjoint events, there's no overlap. They have nothing in common. So a red card and a spade are considered disjoint events. But listen to this. If I ask you the probability of a red card, you know the whole deck has half red cards. But I tell you, it's a spade. So the fact that I told you it's a spade changes the probability of it being a red card to 0. So again, the fact that it's a spade changed the probability from 1/2 to 0, the probability of being a red. And now, by definition of independence, the probability has changed. So red and spade, which are disjoint events, are not independent. So that's how that works. So we can say, no, disjoint events are never independent, because once you have one event, once I know it was a spade, it changed the other probability to 0. Hence, not independent. All right. Now the last one is asking about this hot streak. And so I kind of wanted to explain to you about a roulette table. If you know what a roulette table is like, you have a circle that you spin around the roulette, and there's a little ball that drops onto the spinner, and it lands in a place. Well, usually about half of those are red sections and half of those are black sections. So the probability that you're going to get red is about half, and I think that's not exactly right because I think there's one green one in there somewhere. But anyway, you spin it 5 times, and every single one of those times you get a red. Your ball lands in that red section of that roulette wheel. So it lands there in that section. And so you're thinking, all right, I definitely should keep this going. I am on a hot streak. The ball is loving those red ones. So let's keep this going. Well, do you think that since you have been landing on red, that the next one is going to be red? Do you think the next one's going to be red? Well, that is not necessarily. Because when you spin a roulette table or a roulette wheel, the next spin has nothing to do with that first spin. It is exactly the same chance as the previous one, and that is because they are independent of each other. So who cares how many times you've spun it red? The next one is still the same probabilities. So, in summary, no, because the law of large numbers says, even though the law of large numbers says in the long run you're going to get 50% of each, but we know each one's independent. So since they're each independent, we then know that there's no changing of those probabilities.